Cô nói là
So today we're starting our journey of actually building a computer. You've probably all heard that computers internally only have zeros and ones. And the reason that they only have zeros and ones is because that's what they can get the expression of, not how to evaluate one. For example, I can define only a finite the second row, values of x and y is, and the dual law. Now all these laws can be easily proved if you wish, not if you. If you have x and y or z, that turns out to be exactly equal to x and y, all that, or x and z. Now, as opposed to the usual arithmetic, where we only have a distributed law of multiplication over addition, here we have both the distributive law of and over or, and the dual law of distributive law of or over and. The same trick works if you want to do x or y and z, that's x or y and x or z. Now, there are also laws called De Morgan laws that govern how knots work, how they interrelate with and or. These are laws are called De Morgan laws, and they say the following interesting thing. If you take x and y and do a knot on all of that, that's equivalent to first doing knot of x and oring that to knot of y. And we have the dual one that if you have knot of x or y, that's exactly equal to knot of x and knot of y. Now, all these laws can be easily proved, if you wish, not if you wish, really proved by simply listing all the possibilities in a truth table and verifying that they get the same truth table for the left-hand side and the right-hand side.
yeah.
Now, there are a bunch of other laws, and we can use them to actually do manipulations on Boolean algebra. So, for example, once we have a formula, for example, the formula that you see here, not of not x and not x or y, for example, it could be any other formula, we can now start applying some of these identities to change its form, to simplify it, or to just to bring it into a different format. So, for example, the first thing we can do here is look at the second part, the last sub-expression, the not x or y. We can use De Morgan law here and basically convert it to not x and not y. Now, if you look what we have here, we can use the associative law, because we have not x and not y. We can change the order of doing the and. And we get another expression which is identical using the associative law. At this point, we have something really interesting at the beginning. We have not x and not x. That can be just simplified to not x. Why is that? Because we can actually see also, that's another identity that we didn't explicitly list, but it's easy to verify in the same way that if you take any value w, in our case w is not x, and do w and w, that's completely equivalent to w. Now, this is called the idempotence law, and we can thus simplify the previous expression by simply removing one of these w's, one of these not x's. Now we're ready to use De Morgan law again, and now we got into not x or not y. Now again, here's another law that we didn't list explicitly, but you obviously all know that not x is always equal to x. So using double negation law, we can simplify that to x or y. So that just gives you some kind of a demonstration that you can basically just manipulate Boolean expressions, sort of like you manipulate arithmetic expressions in elementary school. There's another way to get the same conclusion, the same equivalence, without actually going through these algebraic manipulations, simply by actually looking at the truth table. We take the expression, we build the truth table for it, and we've already seen how to take an expression and find its truth table, and then we get the truth table that you see on the board. Now, once you have this truth table, you can say, I know this truth table. This is exactly the truth table of the OR function. And then that immediately proves that the expression on the top is completely equivalent to x or y, as we've derived using algebraic methods previously. Now, of course, it's not completely, you won't always be so lucky to do some kind of big truth table and recognize what it is and immediately see a better and nicer and simpler expression that gives you the same table. Sometimes you will have to do algebraic manipulations, but on the other hand, it's not always true that algebraic manipulations are easy to do in the sense of finding a very simple expression. So, but in general, in principle, you can use both of these methods to actually simplify Boolean expressions or find alternative forms that give you the same Boolean expressions. So we've just finished our first unit describing how to manipulate logical values. Notice that we're still keeping our abstract point of view of just logical values and not thinking about any physical realization that we will have inside our computer. In the third unit, we'll actually switch our point of view and start talking about the same kind of phenomena, but from the point of view of real chips and real gates that we have inside a computer. But before we get to that, in the next unit, we'll keep maintaining our theoretical point of view and start talking about the following problem. How can we construct a function from basic operations? How does that, this is exactly the kind of things we will need to do when constructing hardware. We know what it wants to do, but we'll have to actually construct it from Boolean operations, and we'll try to see how that is done, first from a theoretical point of view in the next unit. So in the last unit, we talked about what are Boolean functions, Boolean values, Boolean algebra, Boolean formulas. What we want to do now is actually talk about how we can construct Boolean functions from more primitive operations. So we already saw two ways to represent a Boolean function, a Boolean expression and a truth table. We also already know how to go from the expression to the truth table. You take the expression, evaluate it for each possible values of the input bits, and then you can fill the truth table. What we want to do now is exactly the opposite. You start with a description of a function, let's say given as a truth table, and our challenge is to come up with a formula that computes the same Boolean function. Why do we need to do that? Well, that's exactly what we have to do when we come to design a computer. We know what we want to do, we know what we want a certain unit to do, but then we actually have to compose it from primitive gates, from primitive operations. So let's see how we can do it. So again, we continue with our abstract treatment. We're trying to see what is the basic logical way we can actually construct such a Boolean function from primitive operations. Later, once we actually talk about practically constructing them, we will be more practical oriented, we'll go step by step and so on. At this point, we just want to make sure what are the principles. So let us start with a specification of a Boolean function given as a truth table. How can we construct it? Well, here's what I'm going to describe to you is a standard way of what's called constructing a disjunctive normal form formula for it, and it goes like this. We actually go row by row in the truth table. We focus only at the rows that have a value of 1. For example, the first row here has a value of 1. Now what we can do is we write an expression that basically gets a value of 1 only at this row. For example, so in particular, since here in this row the values of x, y, and z are 0, 0, and 0, if we look at the expression not x, and not y, and not z, that is going to be a Boolean function, the green Boolean function, that only gets a value 1 on this row. So now we have one Boolean function. We do the same thing, we construct another Boolean function, another clause, for each row that has a value of 1. So for example, there's another second row with a value of 1. This time, in here, this row, y equals to 1, while x and z equal to 0. So the clause we write here is not x, and y, and not z. Again, this is something that completely gets a value of 1 only on this row, and gets a value of 0 everywhere else. We do that for every possible row that has a value of 1. Now the purple row. Now we have a bunch of different functions that each one of them gets a value of 1 only at its row, and gets a value of 0 in all other rows. But we desire a single function, a single expression that gets exactly the value 1 exactly on all of these rows and 0 on the other rows. How do we do that? Well, that's very simple. We just OR them together, and now we get a single expression, a single Boolean function that gets value 1 exactly on the rows for which we built clauses for, and gets 0 everywhere else. And now we basically constructed our function as a Boolean expression, only using ands, nots, and ors. Now, of course, once we have this expression, we can start manipulating it in various ways. This is one way to write the function as an expression, but if you actually look at it, you can see that we can start changing its format. For example, if you look at the first two clauses, you can see that one of them is not x and not y and not z, while the other is not x and y and not z. Notice that we have both possibilities for y and exactly the same fixed value for x. So instead of these two clauses, we can combine them into one clause, which does not ask about y and only asks about not x and not z. So we get an equivalent expression that's slightly shorter. There are more manipulations that we can do, let's not go into them, but we can actually write the same expression in many different ways. Some of them will be shorter than others, some of them might be more efficient in terms of when we actually go to implement them in a computer. But the point is, logically, they're all completely equivalent. Now you might wonder, how do you actually find the shortest or most efficient formula that's equivalent to the one we've just derived? Well, that's not an easy problem in general. It's not easy for humans, nor is there any algorithm that can do that efficiently. In fact, this is an NP hard problem to actually find the shortest expression that's equivalent to a given one, or even to verify if the expression that you're given is just a constant 0 or 1. What's more interesting, what I really want to focus at this point, is that we've really proved a really remarkable mathematical theorem that any Boolean function, it doesn't really matter on how many variables and what the Boolean function is, can be represented in an expression using only the operations and, or, and not. Now, to notice how remarkable that is, just think about Boolean functions on integers functions that you've learned in elementary school. Not every function on integer numbers can be represented using, let's say, addition or multiplication. In fact, most functions cannot be represented just by arithmetic operations. Yet, because of the finite world that we live in the Boolean algebra, every Boolean function can just be represented with and, ors, and nots. And that is exactly what gives us a basic power to actually construct computers only with these possible gates, only with these possible operations and, or, and not. But do we really need all of them? Well, here's a better theorem if you wish. We don't really need OR gates. Just with ands and nots, we can construct any Boolean function. How can we prove that? Well, we already know that if we have ORs, we can do everything. We've just seen that. And now the only thing that we need to show is that we can actually compute an OR with and not gates. But we know how to do that already. We recall De Morgan formulas that exactly give us a formula for OR that only uses not and gates. So now we have a really more remarkable theorem that we only need these two basic operations to actually compute every Boolean function. Can we compute an OR with and not gates? But we know how to do that already. We recall De Morgan formulas that exactly give us a formula for OR that only uses not and gates. So now we have a really more remarkable theorem that we only need these two basic operations to actually compute every Boolean function. Can we go even less? Can we give up, let's say, the AND gate? Well, that doesn't make sense because not only takes one value to one value, doesn't even allow us to combine anything. Can we give up the NOT gate? Well, not really, because AND has this property that if you only feed it zeros, it will always have 0 as output. And there are Boolean functions that when you feed them 0 give you 1 as output, so AND by itself wouldn't suffice. But it turns out that there is yet another operation that by itself does suffice to actually compute everything. So let me introduce the NAND function. So the NAND function, here is a truth table. It gives 0 only if both of its inputs are 1, and every other possibility it gives 1. Logically, x NAND y is defined to be the negation of x and y. So what's so remarkable about this Boolean function? Well, the nice thing is that we can prove the following theorem, that if you only have NAND gates, you can already compute every Boolean function, you can already represent every Boolean function as an expression using just these NAND gates. How do we prove that? Well, we know that if you can do NOT, and if you can do AND, you can do everything. So we just have to show how to do NOT with NAND gates, and how to do AND with NAND gates. So here's how you do NOT. If you just look what happens when you feed x to both inputs of the NAND gate, you plug it into the truth table in the previous slide, and you can see that NOT x is really represented by x NAND x. That's part one. The second part we need to show, how do we do AND? Well, X and Y turns out to be not of X NAND Y. But how do we have not? Well, we just seen that you can do not with NAND itself. So now we've basically reduced the fact, instead of using NOTs and ANDs, we're just using NAND gates. And we got our amazing theorem that just if you have a NAND gate, you can compute everything. And this is exactly what is going to be our approach when we actually go to build a computer. We will give you a primitive NAND gate operation, and you will basically build the whole computer, all the complicated logic that we'll actually ask you to build, using just from these basic NAND operations. So at this point, we've just finished our abstract point of view about Boolean logic, and now we're doing a really interesting shift of perspective from the abstract logical operations to the actual gates and the actual gates from which we build computers. This switch really has there's no actual difference between the two different things in terms of the kind of things that we do, but it's just in the way that we're thinking about them. Until now, we asked you to think about everything as abstract Boolean logic. From now, we're going to start asking you to think about everything as actual little pieces in a computer that computes the functionality that we want.
In the previous 2 units in this week, we talked about Boolean functions, and most of this discussion has been theoretical. Starting with this unit, we're going to talk about how we actually implement these Boolean functions using hardware. In particular, we're going to talk about a general technique called gate logic, which, loosely speaking, it's a technique for implementing Boolean functions using logic gates. Units in this week, we talked about Boolean functions, and most of this discussion has been theoretical. Starting with this unit, we're going to talk about how we actually implement these Boolean functions using hardware. In particular, we're going to talk about a general technique called gate logic, which, loosely speaking, it's a technique for implementing Boolean functions using logic gates. Now, what is a logic gate? Well, a logic gate is a standalone chip, or a very simple chip, or an elementary chip, which is designed to deliver a well-defined functionality. Something like NAND functionality, AND functionality, OR, and so on. What is a composite logic gate? A composite logic gate is one which is made up from elementary logic gate and other composite logic gates. Or simply, it's a more complex gate than the functionality, AND functionality, OR chip, or a very simple chip, or an elementary chip, which is designed to deliver a well-defined functionality. Something like NAND functionality, AND functionality, OR, and so on. What is a composite logic gate? A composite logic gate is one which is made up from elementary logic gate and other composite logic gates. Or simply, it's a more complex gate than the elementary ones. And in this course, we'll develop things like multiplexers and adders. And obviously, most of you don't know what these terms mean. Don't worry about it. You will get acquainted with them and actually build them in the next few weeks in the course. All right, so let us begin with the most fundamental logic gates that we use in this course, called NAND. Here's the definition of a NAND. This is actually the standard diagram that we use to describe a NAND gate. It has 2 inputs and a single output. Everything here is binary, so A, B, and out are either 0 and or 1. Here is a functional description of this gate. If both inputs are 1, we output 0. Under any other circumstance, we output 1. And here's also a truth table description of the same functional specification. Any one of these descriptions is fine. Taken together, what we have here is an abstraction of the NAND gate. We didn't say a word about how this thing is actually working. We just describe what kind of functionality we can expect it to deliver. Okay, moving forward, here are 3 classical gates that pop up in every digital design project. We have an AND gate, which outputs 1 when both its inputs are 1 and 0 elsewhere. We have an OR gate, which outputs 1 when either one of its inputs are 1 and 0 elsewhere. And we have a NOT gate that operates as a converter. And we can put these gates together to create more complex functionality, as we'll illustrate later on. In particular, we can use these gates to create composite ones. So, for example, here's a 3-way AND, which is an extension, if you will, of the simple 2-way AND. And one way to build it is to use this trick here. We can take the output of one AND and feed it into one of the inputs of another AND gate. And if we wire everything correctly, this gate is supposed to deliver the required functionality. What we see in the dashed line rectangle around the implementation is a documentation of the interface of this chip. So the user lives outside the dashed rectangle. So the user sees only the 3 inputs and the output, as you see in the left-hand side of the gate description. If you want to go in, or to sort of open up the black box, you have to see what is documented and done inside the dashed rectangle. So with that, I would like to say a few words about the notion of interface and implementation. The gate interface is the gate abstraction. This is how the user thinks about what the gate is supposed to do. Interface answers the question, what? At the same time, if you want to understand how the chip is doing what it's doing, you have to go deeper and go in. Well, I'm not sure that deeper is the right word, but you have to go to another level of detail in which you actually the black box opens up and you see how the chip is actually constructed. Or you do it yourself, if your job is to be the person who is actually realizing this abstraction. Now, the interface of the gate is unique. There's only one way to describe the gate's functionality. Otherwise, if there's more than one way, either you're not describing it well, or you're confusing the user, because there should be only one unique way to describe what a gate is supposed to do. At the same time, there may be several different implementations that realize the same abstraction. And some implementations may be more elegant, they may use less energy, they may be less or more